just going to carry on from where we were last time. So I'm going to remind you what EM is. It's 2 steps. So the EM algorithm is first we compute this thing. That's the expectation of, and usually when I say this with words, I usually say log likelihood right here. But it's some function that you're playing around with that has a missing component and some parameters you want to learn. I'll write in, because we're statisticians, usually we're playing around with data. I'm really inclined to write this sort of thing because I like the conditionality principle. So likelihood functions adhere to that. We condition on our data. Most statisticians play with this function in this manner. This could be a posterior distribution. And so if I'm about to integrate away psi, it probably is at least partially. So because I'm going to take an expectation with respect to this random variable. And I'm going to condition on old iterations of this algorithm. I'm going to say more about this in a second once we get through this proof that this thing actually works. So the M step, the maximization step, this is expectation. This is maximization. Is we're just going to optimize this function that we just solved. So this is arc maximum. Got to do something to this. Arc max. We're going to do that over theta. And that's my next iteration. So in the example that I'm showing you, we can work this out analytically. So all we're doing is iterating this step over and over and over again. If you can work out your expectations in a tractable manner, meaning you have an equation right here, and you can do calculus or something like that on that equation, and you're just iterating over this thing over and over again. If you aren't able to solve this in closed form, then you do an approximation step up here. So you won't be doing that on your homework. It really is just iterate M over and over and over again. So the problem that we've been looking at, and EM isn't the only gig in town for solving this problem, but it's one such solution, and a lot of people use this solution. I'm going to say my xi's come from a mixture model. And my goodness, we use this term a lot. So mixture models, they're everywhere. So modelers use mixture models. So I'll just remind you, one mixture model that we've studied, at least as a homework problem, is the normal scale mixture model. So if I run a mixture over the scale parameter in a normal, and the weights that I put on the scale parameter are gamma, inverse gamma is really what I'm thinking about, then you get a t-distribution. So t-distributions are normal scale mixture models. And if you're uncomfortable with that, go back to that early homework problem that you solved. If you want to talk more about that, I'm happy to do that. I teach that in some depth in my Bayesian class. So, but T's are hierarchical models where I'm mixing normals with inverse gammas. The mixture model that I'm talking about right now is not a scale mixture model, but I'm mixing over all of the parameters and I'm doing it in an additive fashion. So there's all kinds of ways to mix things. So just like we talk about when we're in the kitchen, we're going to make something, we're going to mix stuff together. How many different ways can you mix stuff together? Sky's the limit. So that this particular mixture model, additive, and we're doing it in a finite fashion. There's infinite mixture models as well. We're really just writing this thing down right here. So I'm going to say my mixture model is fx just like we normally do, I might write in some parameters. That's my bold theta. So just to say this is a whole collection of a ton of parameters. This thing is just k goes from 1 to cap k. So this right here, cap k, is the finite component of this. The summing is the additive part of all of this. And I can just take all of these little distributions, I'll say these can be k different functions, x, and then there's some set of parameters, theta k, right here. So in our example, a normal additive mixture model has all of these written down like this. 1 over 2 pi, there's some parameters in here, sigma k, e to the minus 1/2, we'll say x minus, here's some model parameters, mu k, squared divided by sigma k. Bunker's about to start yelling at me right here, so we better put in those mixture weights, so this is a distribution. I better tell you a little bit about those mixture weights. They sum, come on. So this is an additive mixture model. And since I plugged in a Gaussian function, this is a Gaussian mixture model. Sometimes I change what these little functions are in here. You've got a lot of flexibility to play around with it. Nice thing is this sort of form can almost be used to model anything, any smooth function. So it could be highly skewed or multimodal or whatnot. I can induce those distributions through additive mixture models. Okay, so there's all kinds of questions. What's k, all of that. And so as you ask for more flexibility out of your model, you got to think harder about it. For our class, we're just going to assume we know k. And I've given you at least a few mental exercises on how you might infer k if you needed to. If you ever need to infer k, stop by my office, and I'll tell you how I do it. But there's lots of possibilities for doing this. So this is a Gaussian finite mixture model. We worked out the likelihood function for all of this. So the likelihood, I'll write it down like this, given all of my data. And there's some missing components in here as well. So I've got all my x's, this is my data that I get to observe. And then I have this missing component right here. And generically, I call that psi. So this is just going to be my xi's, x1 to xn. And my psi's are going to be my missing labels. These are my labels. I call these C's. So they're the component labels. Each one of these things are an element between 1 and cap k. So we wrote this down. And this looks something like this. The product, I goes from 1 to n. Sum, k goes from 1 to cap k. And then I wrote down what this little function is right in here. This is just going to be 1 over 2 pi sigma k. There's a pi k in here. And then I have this parametric form. E to the minus 1/2 xi's minus uk squared over sigma k squared. And I need this indicator function. And I'm going to write this down just a little bit differently than I've written before. So after I write down notation and it becomes a little bit cumbersome, I usually simplify and I tell people what it means. So this is the indicator that xi came from component k. So that's my likelihood function that we worked out. I could write this out a lot differently, and I could throw that the indicator up into the exponent, take logarithms of all of these parameters right there, and throw them up into the exponent. We did that last time. And 5 of you stuck around for a little while, trying to convince yourself that this likelihood function that we wrote down is exactly that thing. And after you stare at it for enough time, you go, they're exactly the same thing. So I'll just rewrite that. We got rid of this pretty early. Don't need that too high. You'll start throwing away your constants eventually pretty quickly. So this is just going to look like product I goes from 1 to n. We wrote this down in product form. K goes from 1 to cap k. E to the minus 1/2 xi minus mu k squared over sigma k. Just throw a big brace on this so you can tell what's inside of the exponent. So everything that I'm writing down is inside of the exponent minus log sigma k plus logarithm pi k. So I've just taken these things, thrown them into the exponent. If I'm going to exponentiate them, I better take the logarithm first. And then I have this other bit right here. So I'll say this whole thing, I'll put this in brackets so you can see everything that's going on. This is still in the exponent right here. This is going to be my indicator function. So my indicator is just a switch, turning things on and off. And so I have it in product form right here, and so it's just multiplying this by 1 or a 0. When I multiply it by a 0, it turns e to the 0 into a 1. So there's only one term that shows up in this big product form. Somebody asked me, if I took the logarithm of these things right here and I threw them into the exponent, why didn't I take the logarithm of the indicator function? Anybody have a good answer for that? Bunker?
It's not defined at 0.
Yeah, exactly. It would be a nonsensical calculation. So it'd blow up on you. Again, I'm just using the indicator function as a switch, turning things on and off. So here's how I do it in product form, and here's how I do it in additive form. I think about the model more like this. I don't really think about it like that, but they're exactly the same thing. So it's just you get used to writing things down in different ways for different reasons. So I can throw these products back into the sum right there, take the logarithm, and compute this thing, and it's not too difficult. That's what we did last time. So we wrote down our function q after we did all of this. Again, when we take our expectation over everything, the expectation is only operating on this, because our expectation is over the missing stuff, which is the c's. And so we wrote down q theta given theta t is going to be equal to double sum over I goes from 1 to n, k goes from 1 to cap k. I almost wrote this down last time. I actually made a mistake. I'll tell you where the mistake was in just a second. Plus logarithm of pi k sigma k. And then I have my expectation of my indicator function. Ci is equal to k. So the expectation, once I take it over everything, it only appears right here. And that expectation is going to be over the Ci's given all of my model parameters, theta t. My model parameters are the mu's, the sigmas, and the pi's. And I'm going to index them in t. I almost wrote this down correctly last time. If you go back to the notes, you'll notice that I multiplied this minus 1/2 by all of that stuff. I have my brace in the wrong place. The minus 1/2 is only multiplying this piece of everything. So just go back and correct your notes. And this should be the Q function that you're going to plug into your computer. Before you plug it in, you're going to probably try to optimize this thing. Write down some analytical form where you can figure out what the maximums are. So you're probably not going to plug in this function. You're going to do a little bit more math right here before you program it into your computer. So I'm going to walk you through some code in a moment.
So for this Q of theta, could all of the parameters be like mu k of t and sigma squared k of t?
Say what?
For this Q theta, given theta t,
Yeah.
should it be like mu k of t and sigma squared k of t and?
Yeah, it's all of those. That's what theta is. So I'm kind of generically notating theta as just all the things I don't know.
So when we say argmax theta, it's argmax of mu k, sigma k, and
Absolutely. Yeah, that's what we're going to maximize. And I'll walk you through that in just a second. But yeah, that's right. And I should just mention, this has to be done for all of the k's. That's my notation for that. Yeah, so theta generically means the mu's, the sigmas, and the pi's. So a little bit of generic notation right here. But we know it means. So if I have a bunch of parameters and they're smooth and I want to optimize them, what I do is I take the partial derivatives with respect to each one of them. I set them all equal to 0. I come up with a system and I solve that system. It turns out, I'm just going to show you this, that all of these maxima that we're going to find can be written down in closed form. And they're all right there. So I've written it down high-dimensionally so that I'm not just working with scalars. So xi's could be multi-dimensional. They could be coming from a multivariate Gaussian. And I want you to play around with that in a simulation study. So I'll write down what these things are in just a moment, but I just want you to see that we can write these things down in closed form. So my cap sigma is a covariance matrix in this case. And how do I evaluate my covariance matrices? Empirically, I take an outer product. But in this case, I have a weighted form of that outer product. I'll say something about that in a moment. But I've written down at least what the maxima are. So when you maximize this equation right there, then the maximums are given by those equations. And that's what you're going to plug into your computer and program up. So EM, you do a little bit of math up front, you program that into your computer does all the trivial solving for you, over and over and over again. So, let me just show you. So I wanted to take the maximum of this thing right here. So what we're going to do is we're going to maximize expectation of an indicator. We went through this last time. This is the probability that xi came from component k. So how do I do that right there? I want to be specific about this. When I say this, I also mean I've got the data. So when I write everything down, I've got the data in hand. Which data is informative about the given all of the model parameters? What data is informative about xi being in component k? Only one data point. Only xi is going to help me with that. So this thing right here is going to be my fxi. So I should probably write some conditioning on xi so it appears in the equation, but I've been a little bit lazy. What I mean right here is xi comes from component k, meaning that I've got model parameters coming from component k right here. And if you'd like me to write this down, ci is equal to k, that'll probably make Bayes' theorem look a little bit more obvious to you. So I like to sometimes write that into everything because it looks like Bayes' theorem. So times my probability that ci is equal to k, right here, divided by the correct normalizing constant. K goes from 1 to cap k. fxi given mu k, sigma k, ci is equal to k. And just to be super redundant about all of this, my fxi given mu k, sigma k, ci is equal to k, this is going to be proportional to e to the minus 1/2. Then I write down my sigma in here. Sigma k e to the minus 1/2 xi minus mu k squared over sigma k squared. So I'm just taking this thing and I'm plugging it in. Proportional to, I remove my 2 pi's so that I don't program them up on my computer, evaluate them. Wouldn't slow down the code too much. So that since they cancel in this equation, I'll just get rid of them up front. Okay. So we've got these probabilities right here. This is the Bayesian twist in the algorithm. Okay, so I want to maximize this thing. I've got some probabilities right here. I'm just going to give myself a little bit of notation to play around with. I'm going to call this pi I k. And I want to be specific about this, that everything that I'm doing is going to be conditional on the last iteration of the algorithm. So which mu k's, sigma k's, am I plugging into this equation? I plug them in at the last iteration. So I might write down that this is at the t iteration. When we go through the proof in just a second, it will become clear to you what we've done.
The denominator, the summation, should there be probability of ci equals k?
Yeah, we need those. Absolutely. This is good. My probabilities of the CIs is equal to k is in there as well. And I'm calling this thing pi I the t iteration. Yeah, absolutely. Okay. I can rewrite this equation just with this suppressed notation right here, calling this thing pi I k at the t iteration. So let's say I want to maximize this function that I'm playing around with. Let's do the hard one. Let's maximize this over the pi's. So I've got this parameter floating around in here, and I want to evaluate what I think its maximum is. I just want to be specific. This is the class probability in the original equation. So that's this thing right here. This pi I k is the class probability for individual xi's. They're different. So given the mu's, sigmas, here's where I think the xi came from. This is the probability of that label. This is the overall probability of being in a particular class. They're different things and we treat them differently. They obviously have something to do with each other. So if I'm looking at Q in all of this, and I go and I start taking derivatives with respect to pi, this part right here doesn't have any pi. So as soon as I hit it with the first derivative, it goes to 0. No pi's there. Same thing over here. And the only part of my equation that shows up and is going to have any impact is this part. So if I want to maximize Q over the pi's, I can just get rid of all of this stuff right here. And I'm going to just zero those out to begin with. As soon as I hit them with the derivative, they're gone anyway. So I'm going to wind up with this equation right here. Let's just do k is equal to 2 for this example. That's probably where I should throw in my superficial, part of this equation, and I'll generalize in a moment. But what I'm going to wind up with is I'm going to have sum I goes from 1 to n. And I'll just have 2 terms in here, because I'm going to be talking about this specific one where k is equal to 2. What I'm going to have is I'm going to have log pi 1. And this is going to be times pi I 1. So the kth iteration. So that's this thing right here. So I'm taking that and I'm multiplying it in, getting rid of all my other terms, plus log pi 2 pi I 2, the kth iteration. So I'm going to maximize this thing. So I want to come up with the arc maximizer over the pi's, pi 1, pi 2. Because I'm only thinking about the pi's, I can get rid of everything else. When I go to find the mu's, I can forget about that term and that term. When I'm going to figure out what the sigmas are, I can forget about that term and that term. Hopefully that makes sense. If you want to write everything down, you can, and then take the derivative of it. But this is the part of the equation that you're going to be maximizing. I have to remember that there's a constraint in here. So pi 1 plus pi 2 is equal to 1. So Lagrange multipliers is kind of a trivial technique for adding in the constraint. You could just add the constraint before you do anything. That would be fair game. So instead of Lagrange multipliers, this turns out to be equivalent, I'm just going to take that parameter and write it in with respect to the constraint. And I'm just going to write it as pi 1. So pi 2 and pi 1 sum to 1. And so this is a way of just including the constraint up front. If you go back to your old calculus class, this is what Lagrange multipliers does for you. It adds your constraint to the system of equations that you're solving. That's all it does. I'm not going to say too much more about that. But I can just add that in. So here's my constraint, and I just plug it in. I probably need to adhere to these things being positive, but since everything in the equation is going to be positive, it happens naturally for us. But if you got a negative solution, you should probably think about that a little bit more. So taking derivatives of this whole thing isn't too hard. So what I'm going to do is I'm going to take the derivative with respect to pi 1 of this equation right here, log pi 1 pi I 1 t. I goes from 1 to n plus log 1 minus pi 1 pi I2 t. You could write these in. This is going to be the complement of those things. They sum up to 112. And I'm going to set it all equal to 0. So I'm going to evaluate this at pi 1 is equal to pi 1 hat. So, and then I'm going to take this thing and I'm going to set it equal to 0. And I'm going to solve for pi 1. So the derivatives aren't too hard to work out. So this is just going to be sum I goes from 1 to n, 1 over pi 1. So I know what the derivative is of log pi 1 times pi I 1 t plus derivative of this thing, 1 over 1 minus pi 1. Need the chain rule. So negative. That's going to put a negative sign on here once I take do the chain rule times pi I 2. And I'm going to set this equal to 0, and as soon as I do that, I throw hats on everything. And then we're going to solve for pi 1 hat. Okay, so a little calculus lesson thrown in. We shortcutted a lot of this. You guys know how to do this stuff. At the end of the day, once you solve for pi 1, it looks like this. Pi 1 hat is equal to the sum of pi I 1's t over n. I goes from 1 to n. So it's the average of these probabilities. So what's the probability of being in class 1, component 1? It's going to be the average of all of the xi's probabilities of being in that component. Kind of makes sense. So you might have guessed this to be the case. I also want to be specific that I've iterated this over t. So I'm going to plug my t right there. I've thrown down the other maxima. For this homework, you'll solve for this. So you'll do the exercise, carry it out, show me the steps of your calculation, or at least convince me that you know how to take this maximum. What you're going to wind up with is that your mu's, UK's, are going to be an average of the x's, just like we normally do. This is going to look like sum I goes from 1 to n, xi's, and usually we end up dividing this by n. We're going to do something a little bit different. We're going to take a weighted average. This is going to be my pi I1's right here. At the tth time step, and I'm going to divide it by these same weights. So this is a weighted average. I goes from 1 to n, pi I1's. So this is a weighted average. I just want you to do a sanity check real quick. If I knew with certainty which components were responsible for each xi, then these probabilities would be either a 1 or a 0. And this would be x bar for that sub-model class. So work through that in your head. But this would be the, if you did know all the component labels, you wouldn't have a probability right here, and this would be your x bar. You would typically compute. Similar for sigmas. This is going to be sum of the xi's minus my mu kt. Take this thing and plug it in. You can throw a hat on there if you want. Square this thing out. I usually divide by n or n minus 1 or something like that. Instead, we're going to take a model averaging. So this is an average with respect to these weights. So sum of pi, k. Oops, I should put k right there. In high dimensions, bigger than one dimension, those are those equations, like that. So what you do in EM is you just iterate over these equations. Boom, boom, boom. So let me just write down what EM does.
Oh, on the bottom of the mu k, should that be finite kt?
Yes. We need to know which ones we're talking about. Yeah, absolutely. So this is what EM looks like for this problem. For t goes from 1 to cap t, I'm going to iterate over something. This is some big number. Big. What's big mean? Until you converge. So you can look at the iterations, and once they settle down, you can stop iterating. This is going to just look like this. And what I'm going to do is I'm going to compute all of my I goes from 1 to n. I'm going to compute pi I k's. How do I do that? I plug everything into this equation. So I evaluate this thing. And I do that for each one of the k's. K goes from 1 to cap k. So I get all of these probabilities. You can think of this as a big matrix in your form. Probably store it like that. Then with all of those, I would end up computing my mu's. T's are going to be equal to these things right here. And I'll write down that this is star k. Mu k's, and I'm going to end up doing this for k goes from 1 to cap k. And then I would do the same thing for the sigmas. And I would plug everything into this equation. So star, star. I just iterate. I keep doing it. Peter.
Do you need individual message formulas for both of those, or do you do them all in first message form?
It depends on how you code it up. If you vectorize it in R or MATLAB, you don't need to use for loops. I'm kind of imagining that this is for loops. So when I write out my pseudocode in my head, it always looks like very slow C code. But yeah, you probably vectorize it and just throw that thing into a big vector and evaluate it all at once. It'll do a whole like thread buffer if you do it that way, which is cool. It speeds everything up. If you don't do it that way, your code will just run slower. And in this class, I don't really care. So in your life, however, you're digging into it. You're using all your time waiting for your codes to converge. So we have better things to do with our lives, so probably write it more efficiently. At least at some point. So what I'm going to ask you to do for this homework is basically study this mixture problem over various mu's and sigmas and different dimensionality. I don't give you a specific instruction on the homework. So you might say, how many different examples do I need? I'm going to say enough to convince me that you understand when this thing works and when it does not work. So as the modes get closer and closer together, that's obviously relative to the sigmas. The algorithm has a harder time figuring out what the truth is. And in high dimensionality, harder time becomes even worse. So there's some breakdown points. So I want you to study enough examples to probably do it in less than 10. So draw me some plots, compare those plots to each other. Box plots are usually a good thing to report, and write down your conclusions. So show me some examples where everything works, and show me some examples where things don't. That's called the rest of your life. So that's what we do. Let me show you some code. I coded this up. I'll post this code online for you. It's written in kind of a slow C fashion. In this code is incomplete. It only works in 1D, and I assume I know what the sigmas are. So I give myself the advantage. This code is only updating the pi's and the mu's. And k is 2. So I wrote a very, very simplified version of the code that you'll be playing around with. So I get to input the truth. So just real quickly, my mixture model is that. So mu1, mu2, unknowns, p is a probability. Because of the constraint, there's only one pi. Pi 2 is 1 minus pi 1. So, because of that constraint. So my example is a little bit too generic. You'll show me more general versions of this code. I don't actually need to see your code, I just want to hear about the results. Okay, we can plug in some truths right here so you can play around with this. I've already put it in here. Mu1 is 2, mu2 is 10.5. My variance is 1 in all of this, and my probability, pi 1, is 0.7. So pi 2 is 0.3. I'm going to run this thing. So it generates some data. The data that I generated is this 2-component mixture model. It looks like that. One of those histograms is higher than the other one. That's because that's component 1 and it has probability 0.7 compared to probability 0.3 being in the second mode. That's what's distinguishing the height differences. So my algorithm is just basically iterating over these steps. Update all of my probabilities, and then update my mu's. And that's it. So pretty short. So a little math up front, and the code is pretty quick to evaluate. So when I ran it, I show you all of my iterations. We can look at those a little bit slower in a moment, but it converges to something like mu is 10.4 in 2. Remember what my true mu's were, they're 2 and 10.5. That seems to do a pretty good job. And my p's are 0.323 and 0.677. So pretty close to the truth. Again, we don't get to see the truth. We get data that helps us hone in on the truth. So we're pretty good. I'm going to rerun this again. And that's what I do with iterative code is I rerun it again. Let's do it again. So 0.3, 0.69, 10.4, 1.9. Pretty close to my old answers. Anybody notice anything that just happened?
That's making the same thing over and over again?
It did it. But now I got 0.7 and 0.3. Do this again. Getting closer, I guess. I mean, it's in a mode. There's lots of little local modes all over the place. So 0.2, 0.7, 0.28, 0.7. Now I've got 0.7, 0.29. They're flipping. The 0.7 and the 0.3 just exchanged roles. Your code has no idea what component 1 and component 2 is. And so it labels it arbitrarily. This is called label switching. And so sometimes you hear people talk about that. Label switching is a big problem. We had a colloquium where somebody talked about label switching many times. So you need to be aware that the labels are arbitrary. So what you called component 1 and component 2, you could have called component red and component green. There's no order in these things. So be aware of that in your code. EM doesn't have an automatic fix for label switching. No code does. We'll have to come up with some sort of heuristic to deal with it. If you want to know how I deal with label switching in practice, come and see me, and I'll tell you what I do, so that I can get my code to operate the same way every time I run it. So I'll post that for you. I think the only thing we're missing right now is a proof that all of this is supposed to work. We have a demonstration that it works, but next time we're going to come in, spend 10 minutes proving this. Proof is not in the book. But I just want to be specific about what we need to prove. So remember what our goal is. Our goal was to maximize over theta this integral, f theta psi, given my depth, and I integrate over psi. So I want to solve that problem. So that's what we're doing. It's kind of interesting. What we've done is we basically set up a fixed point maximization problem, and I'll say a few things about that when we carve through this proof, as to why I carry the iterations from step to step. But we want to do this, and our way of doing it is to maximize a different function. So we're not doing this explicitly. We're maximizing Q's. And we're going to iterate. And this thing right here is a different function altogether. Psi given theta t log f theta psi given data. So the book doesn't give you much insight on this. It says in order to maximize that thing, let's maximize that. That's a big leap. So I want to come in next time and show that the solution to this problem is the solution to that problem. So we'll write that down. You might want to brush up on Jensen's inequality real quickly, but I'll just show you the steps that we're going to do real quickly so you can think about these. So I'm going to call this function right here f theta. So I'm going to get rid of my data notation just to clean this up a little bit. And I just want to show you that f theta, let's write it down like this, f psi given theta is going to be equal to f theta psi divided by f theta. Keep in mind, all of these are conditional on the data. Everything's conditional on the data. I'm just going to suppress the notation a little bit. And so this right here is the margin, so I'm taking the joint, I'm dividing by the margin, and I'm getting the conditional. Calculation we're all used to. So f theta is going to be equal to f theta psi divided by f psi given theta. What we're going to do is we're going to take expectations over this thing. This expectation, I'll just write it out like this. Expectation of, oh, and I should probably do this real quick before I take the expectation. If I take the logarithm, it doesn't change anything in terms of what I'm maximizing. I want to maximize this thing. Take a logarithm, it's still the same maximum. So I just want to point out what EM is doing. We'll work through this a little bit more formally. So if I take the expectation of log f theta with respect respect to psi given theta t, right here, this equation right here doesn't depend on psi. The left-hand side doesn't have psi's in it. So what is this thing? This is just log f theta. So the left-hand side of this equation is what we want to maximize. But the right-hand side looks like this. Once I take the logarithm, it's going to break this into a difference. We'll do this slower next time. This is going to be log f theta given psi minus the expectation of the logarithm of f psi given theta. So I just want to point out, again, our goal is to optimize the left-hand side. EM is only dealing with this. So again, this is psi given theta t. This is psi given theta t. So when we go to EM, this is Q. EM is forgetting about this term. And what we'll come back and show is that this function doesn't matter to us right here. And we converge faster if we just deal with that. So I'll make some statements about that next time. It's just a little bit of math. It includes Jensen's inequality. So this doesn't depend on size. This stuff does seem to have the size in there, and EM is optimizing this thing. It has something to do with this. What we'll show next time is this is a decreasing function no matter what we do to it. That's it for now, you guys. Come back with a proof, and then I'm going to move on to invariance of the maximum likelihood estimator, and then we're going to jump into Kramer route. That's our progression. Thank you, guys. I'll see you on Monday.